Hi, everyone. I'm Apurva, and I'm an AI developer advocate here at MongoDB. I'm tuning in from sunny California today. I just moved closer to a beach, so I have a nice view of the beach today. Curious to hear where everyone is tuning in from, so put that in the chat. Today, I'm going to talk to you about a retrieval technique called parent document retrieval. We'll talk about when to use this technique, how it works in MongoDB, and finally, see how to implement it using MongoDB's LangChain integration. I wrote a pretty detailed tutorial about this a while ago. It's linked or will be linked in the video description, so feel free to check it out after. But yeah, for today, the way this is going to work is I'll quickly go through some of the key concepts from the tutorial, and then we'll recreate and walk through all the code in the tutorial live as well. Does that sound good? I hope so. And yeah, I'll keep stopping every once in a while to check for comments and questions. So if you have any questions as I'm going through stuff, definitely put those in the chat. I'll be checking. So yeah, first let's talk about when and why you'd use parent document retrieval, right? I want you to look at this section here. So essentially, when chunking documents for LLM applications, there are often conflicting considerations. You want your chunks to be small enough so that you have good quality embeddings, but also you want chunks to be large enough so that they can capture enough context. And this is difficult to achieve when using a single chunking strategy with a predefined chunk size, like they normally do in the simpler techniques. And this is where parent document retrieval comes in. So in this technique, you store and embed small chunks at ingest time, but at retrieval time, you fetch the source document or larger chunks. And this results in this effect of context expansion at generation time. And some use cases for this technique include, say, documentation chatbots, where a user might ask a question about authenticating to a particular API, for example, like trying to troubleshoot the authentication. So if you want your chatbot to not only answer the exact question, but also provide peripheral context about, say, token expiration and refresh mechanisms from the same document, you might consider this technique. Now let's quickly talk about how this works in MongoDB, because I'm going to show you how to implement this technique in MongoDB today. So we'll be using our integration with LangChain, but I think it's still important to understand what's happening behind the scenes in case you want to tweak and customize it outside the integration. So this is how it works. At ingest time, given a document, it splits it up into chunks using whatever chunking strategy you choose. Then the chunks are embedded and ingested into a MongoDB collection. Each chunk document also has a parent ID field attached to it, indicating the parent document that it came from. And finally, the parent documents are also ingested as is into the same collection that the chunks were ingested into. And then this is what things look like at retrieval time. So the user query is embedded, and the chunks that are the most relevant to the query are retrieved using semantic search or vector search. But it doesn't end there. There's an additional step here. So using the parent ID fields in the chunks, we also retrieve the parent documents themselves from the collection or parent chunks. And instead of passing the chunks to the LLM as context, we pass these parent documents to the LLM as context for generating a response. So yeah, that's kind of the high-level overview of what this technique looks like. I'll pause here to see if there's any questions coming in before proceeding on to the live coding section. Let's see. Hello from Uganda. Hello from Brazil. Bonsoir. Are you French? Okay. Right. I don't see any questions for now, so I think we can move on to the live coding section. So yeah, like I mentioned, we are going to be implementing this technique using MongoDB's integration with LangChain. So let's get started with that. So the first, I've done a few things just to like get the prerequisites ready. So I've installed the packages I need. So datasets, which is a package to download datasets from Hugging Face, PyMongo, which is MongoDB's Python driver, LangChain, which is the core LangChain library, LangGraph, which is a Python package to orchestrate LLM workflows using this new, well, not so new anymore, but orchestration framework that LangChain came out with a few months ago. Then LangChain MongoDB, which is our integration with LangChain, and finally LangChain OpenAI, because I'm going to be using a couple OpenAI models in this live code. And then the first thing I'm doing is just like setting any environment variables and things like that. So these imports here, first thing I want to set is the OpenAI API key. I've already said that just so I'm not pasting secrets on the live stream. And then this is where I'm setting connecting to my MongoDB cluster. So all you need is to grab the connection string for your cluster and then create the client. And then I'm doing a quick sanity health check by pinging my cluster. And there's also this like Hugging Face token I'm setting here. And the reason that I need that here is because I'm using a gated data set in Hugging Face. So this is the docs data set under the MongoDB Educational AI Organization. And this is a data set that we released a while ago, and it's a subset of our official technical documentation that you see on mongodb.com. And this is a really good data set to prototype things like documentation chatbots or any like production grade RAG application, because this is literally some of the data that we've used to create our own documentation chatbot. So yeah, if you would like to access this data set, all you need to do is request access, and it gets you get access to the data set pretty much instantly and automatically. But yeah, if you want to programmatically access this data set after the fact, then you need that Hugging Face token, which is why I've set that there. Cool. So that's all our prerequisites ready. Let's start by loading that docs data set. Okay. And then, so it's a pretty large data set. I think it has 6,000 documents or so, but I'm just going to take the top 1,000 just to demo things. Okay. Any questions? No questions yet. All right. Let's just preview that data set. So as you can see, it has the date when the data set was updated, date when a particular document was updated, the document ID, some metadata about what type of content, any like page descriptions, the source of where the data came from, and the actual body. This is what's going to be important when we build like the RAG and agentic application later in the tutorial. Okay, so first thing we want to do is convert this data set into LangChain documents. And I'll just show you what a LangChain document looks like in just a bit. So doing that import, then I'm iterating through the rows in my data frame and the content. So there's two things in a LangChain document. Mainly, it's the content and the metadata. And the content mainly is the raw text of that you want to associate with the document, and metadata is any additional informational fields. So in this case, my content is going to be the body of the document itself. And the metadata, for the metadata, I'm extracting a subset of fields from my data set, like the updated date, the URL, and the title of the document. And then I'm going to add those fields to my LangChain documents as well. And finally, creating that document object. So let's run that. And let's make sure this looks right. So this is what a LangChain document object looks like. So as you can see, there's a metadata field, and it has all the fields that I added to the metadata attribute. And then the page content attribute has the body of the document itself. And let's make sure all the documents got processed. That's 1,000, and that's how many documents we started with. So at this point, we've converted our data set into LangChain document objects. So now let's go ahead and instantiate the retriever, the parent document retriever. So again, the imports here, I'm going to be using an embedding model from OpenAI, which is a text embedding 3 small. Also want to set the database and collection that I want to ingest data into. And then I'm going to write this little helper function to do the chunking. So I'm using this strategy called recursive token splitting with overlap. So essentially what this does is it first chunks documents based on a set of delimiters, and they are usually like periods, commas, spaces, that kind of thing. And then it tries to merge those characters into tokens until a specified chunk size is reached. So for example, here I'm saying the chunk size needs to be whatever input chunk size. And I'm also specifying a chunk overlap, which typically we recommend start with like a 15 to 20% of the chunk size. So at this point, we'll hopefully have chunks that have about 1 to 2 paragraphs and some overlap between the chunks. The next, I'm actually going to create the parent document retriever. And I'm going to do this using the from connection string method of the MongoDB Atlas parent document retriever class. And what this does is it automatically creates a MongoDB vector store as well as a document store behind the scenes. So when documents are added to this retriever, the vector store interface splits them into chunks using this helper function, generates embeddings and ingests them into a MongoDB collection. And then the document store ingests the parent documents or parent chunks into the same collection. I'm going to set that. So here you specify the connection string, the embedding model, which is what we defined here, what splitting strategy or chunking strategy you want for the child chunks, the database and collection name to ingest data into. And these are like the arguments that are important for the retrieval piece. So you want to say where the raw text of the chunks or parent documents lies and how many chunks to retrieve during vector search. So I'm saying, give me the top 5 documents. So basically, this has all the parameters required for the MongoDB vector store as well as the doc store interface. And say you didn't want to do parent document, but instead do parent chunk retrieval, where you have smaller, where you're storing smaller chunks, but at retrieval time, you want larger chunks instead of the whole document, then you can also add an additional argument here, which is the parent splitter in addition to the child splitter. So instead of creating small chunks and ingesting the parent documents, you'll ingest the smaller child chunks as well as the larger parent chunks. And those are what will be retrieved at retrieval time. But yeah, for this demo, I'm going to be using parent document retriever instead of the parent chunk retriever. No questions so far. Okay. So now that I've initialized my retriever, I'm going to use that to add and ingest documents to a MongoDB database. So just for fun, I wanted to show you what things would look like if, say, I had a large data set. Like here, I'm working with just 1,000 documents, but when you're building production grade applications out in the real world, typically you're working with large data sets. And this is where you probably want to do like some batch processing and asynchronous processing of your data to speed things up rather than like doing it sequentially, one document at a time. So again, writing a few helper functions to do the asynchronous processing. So first one here is a process batch function, which is going to ingest batches of documents into MongoDB. So the semaphore, if you're familiar with asynchronous processing, this is what tells async IO what the concurrency limit of how many processes should be running at any given point. And I'm also going to use this add documents method from LangChain. So if you're doing synchronous processing, you just use add documents. But because I'm doing things asynchronously, I need to use an asynchronous method for adding documents to the parent document retriever, and LangChain supports that. So that's what this does. And then what I want to do is in each process, I want to process a certain batch of my data set. So in this function, I'm creating the batches. So it's going to iterate through all my documents, and I've specified a batch size of 256. So it's going to yield batches of 26 documents each. And then finally, this is the main function that orchestrates the asynchronous ingest. So creates the semaphore, which specifies the concurrency limits for the asynchronous processing, creates the batches, and then for each batch, it's going to spin off a task to like run the documents through the parent document retriever and finally ingest them into MongoDB. And then we are going to await the results from all the tasks. So no task is essentially blocking the other while processing. And this takes a while, so I'm not going to run this here right now, but I just wanted to show you what it would look like once the documents are ingested in MongoDB. But let's finish this loop first. So creating that collection where I want to ingest documents, deleting any existing documents, and then I'm going to run this process docs function on my full list of LangChain documents. So once this goes through, this is what your documents would look like in MongoDB. So remember, we had 1,000 documents, but now that we've chunked them, we ended up with about 25,000 documents. And this same collection is also going to have the parent document. So let's see if this one is a parent or child document. So it has a doc ID field. So this is a child document because each child document has a doc underscore ID. And if it's a parent document, it's not going to have this field. And I also ran the parent chunk retriever a while ago. So notice that this has more, we ended up with more documents here than the parent doc. So we had 25K here, but if we did parent chunk, we ended up with 35,000 because we have like two types of chunks. So yeah, again, same concept though. Document ID here indicates the parent chunk instead of the parent document that this chunk came from. Anyway, so going back here, so now that we have our data in MongoDB, going back to our code, the next step we want to do is set up the vector search, or basically use this parent document retriever in a RAG and agentic application. But to retrieve documents using vector search, the first thing you're going to want to do is create a vector search index to efficiently retrieve documents from MongoDB. And you can do this programmatically through the Python driver. So I'm just setting the vector index name and the vector index definition. So the definition essentially contains what type of index. In this case, we want a vector search index, then path to the embeddings in our documents, which is just embeddings, the number of dimensions of our embeddings, and this depends on the embedding model being used. We use the text embedding 3 small, and that has about 1536 dimensions. And you also specify the similarity metric, and we are going to use cosine here, but this effectively tells the vector search what mathematical function to use to find proximity, to basically quantify proximity in the vector space. I'm going to set that, and finally create the index. So I just have a try except here to be like, if the index doesn't already exist, then create it. And if it already exists, then don't. So, oh, looks like I didn't run something. Collection. Okay. I know what happened. All right. Okay, so looks like I already had the index, so it skipped the index creation. And now I want to show you two things. First, we'll see how to use this retriever in a RAG application, and then we'll also look at how to use it in an AI agent. Do that, and we are going to create a simple RAG flow. So essentially, the first thing we want to do is retrieve and parse documents. So in this case, we are going to retrieve context, I'm saying pass documents through the parent document retriever. And then this is like some light post-processing that I want to do on the document. So for each doc, I want to grab the page content and just join them to like new lines. And then the question, I just want to pass that through to the next step. And this is what this runnable pass-through does. So each time you want to just pass anything to the next runnable in LangChain, this is what you'd use. And I'm creating a basic prompt template saying answer questions only based on provided context. If no context is provided, respond with I don't know. This is a pretty simple, but to a large extent, effective method to for the LLM to not give you responses that it's not confident of. And then appending the question here. Finally, defining the chat prompt based on this template and the model that I want to use. I'm using a flavor of GPT-4o and specifying that I want to parse the output from the LLM as a string. And then we are going to create that RAG chain using LangChain's LCEL notation. So you want to say first to the retrieve step, pipe the output of that to the prompt, pipe that to the LLM, and finally the parse output stage. Let's run that, and then let's test our RAG chain. So I'm asking it a question, how to resolve alerts in MongoDB. And because I'm using parent document, I'm hoping that it'll give me a more holistic response. So let's see. Okay, let's look at the response to resolve alerts. So yeah, looks like it gave me an immediate solution to my question, but also it's trying to tell me what I can do to implement more long-term solutions, monitor progress, and how to like acknowledge and basically dismiss alerts, and also a little bit about metrics. So I feel like it tried to answer a little more than the immediate question that I asked. And you can see in like customer service scenarios or scientific research or legal case preparation how some of that additional surrounding context might be useful. So now I'll show you how to use the retriever in the context of an agent. Just warnings. All right. So in this case, we are going to convert the retriever into a tool. And that's as simple as using this tool decorator in LangChain. So yeah, basically anything you want, any Python function you want to convert to a tool, just add this decorator, then give a pretty much self-explanatory function name, the arguments to the function, and a description of what the function does, arguments, and its return values. That's basically what you need to convert a function to a tool. So here, same thing that we've done before. So I'm getting the documents by invoking the parent document retriever, doing that simple pre-processing of getting the page content and appending that to a string and returning that context from this tool. So creating the list of tools. And then some LLM stuff. So first thing we want to do is instantiate the LLM that we want to use as the brain of the agent. Like this is what's going to reason through the task at hand and decide whether or not a tool needs to be used. If so, which tool to use. In this case, we just have one tool, but this becomes more important when you have multiple tools. Then we have a prompt for the agent as well. You're saying you're provided with a set of tools to answer questions, think step by step. This is a very easy way to have the agent do chain of thought reasoning. So it'll think through a problem step by step and then determine a plan to solve the task. Also saying do not rerun tools unless necessary. I've seen LLMs do that sometimes where they just get stuck in this like tool calling loop. And yeah, if you aren't able to get enough information, then say, I don't know, you have access to the following tools. So then we are going to partial this template with the tool names. And partial just means like it'll fill in any like placeholders in the prompt template. And then we are going to bind the tools that we have to this LLM. And we are going to do that using this bind tools method. So again, like a very simple chain here, which is chaining the prompt with the LLM that has access to tools. I'm going to be using LangGraph to create the AI agent. And the basic concept here is to create LLM workflows as graphs. So there's three main components of a graph. There's state, nodes, and edges. So the graph state is essentially a set of attributes that all nodes can read from and make changes to. Nodes are essentially, it can be any Python function. It doesn't even have to be a LangChain dependent function. It can be virtually any Python function that basically holds the core logic of what your agent does. So that forms the nodes of the agent. And then edges can be fixed, conditional, or cyclic, and they are just like pathways to connect the nodes to each other and defining the flow of your agent itself. So in my graph state, all I really want to track is the messages, user and assistant messages. I'm going to define that. Then I'm going to define the agent node. So my agent node, like I said, it can read from the graph state. So it's going to read messages from the graph state. And then it's going to invoke the LLM with tools, pass those messages into that. And then the response will be either I want to call a tool, or like if it's done, if it has the answer it wants, then it'll just return the final answer. And then I'm defining the tool node. LangChain has a pre-built utility for converting tools into a node for LangGraph, and that's literally just tool node and then tools. But if you wanted to do anything custom with that, then you'd, again, define a Python function and write your custom logic in there for the tool node as well. Done that. And then I'm actually going to define the graph itself. And that's just basically adding the nodes and connecting the nodes with edges. So initializing the graph and parameterizing it with the graph state that we defined before. Then the first thing we want to do is add nodes to it. So I have two nodes, agents, the agent node and a tools node. And then I'm going to add edges to it. So you can see this like special node here, which is the start node. Essentially, any node that doesn't have anything before it will be connected to the special start node. Then I want basically a fixed edge from tools to agent. And then I want a conditional edge from the agent to tools, because I don't always want the agent to call tools. Like if it doesn't need to call tools, or if it has the final answer, then I just want it to end. So basically I'm saying from the agent node, first do a check on whether or not you need to call a tool. And if you do need tools, then call the tools node. If not, end. And again, end is a special node. Whenever you want to end the processing and don't want any additional nodes after, you would go to the end node. And I'm finally compiling that graph. Cool, graph's compiled. Let's try it out. So again, these are my inputs to the graph. It needs to be a certain format, like it needs to say messages, because that's the attribute that we are tracking in the graph state. And then it needs to be either a user or assistant message. So that's the format. And then I'm going to stream outputs as the inputs go through the nodes of the graph. So I will print out the key, which is to say what node it's at, and the value, which is like what's happening in that node. And then the final answer. Okay, so let's see. So the first time it goes to the agent node, and the agent has determined that it wants to use a tool. So it comes up with the arguments to use and the name of the function to use. And then it's going to call the tool node. So the tool node basically uses the parent document retriever to retrieve the context to answer the question. And then it goes back to the agent node here. So this is the prompt. It has the context now, and it determines that it doesn't need to call any more tools. And it has the final answer, which is, again, to resolve alerts, understand it, view, acknowledge, resolve, unacknowledge. Again, you can see it's a pretty holistic response to the question that we gave it. So that's kind of what I had for today. And I think we have a bunch of time for questions. So let's go take a look at that. Yeah, so if you have any questions, now would be the time. Right, if there's no questions coming in, oh, there was one thing I wanted to point you to. So the code that I was just showing you, it sits in our GenAI Showcase repo, which is MongoDB's generative AI cookbook. it has all sorts of examples of like rags, agents, evals, benchmarks, and a bunch of advanced retrieval techniques, or like quantization and stuff like that. So yeah, if you want to follow up on any of this and check out our other examples after the fact, I'm going to drop the link here. And yeah, give us a star, watch for more content, or fork the repo and build on top of what we have there. All right, with that, I think I'm going to end the stream. I'll see you next time. Bye.